All right, thank you. That thing will go away in a second. All right. Okay, I think people can see my screen and can see me.
Yep.
So I was told that this seminar is about combinatorics broadly construed. So I'm going to stretch that as much as possible because I am some kind of geometer. But yeah, I'm going to talk about automorphisms of the loop and arc graph of infinite type surfaces. So let me give a little bit of background, or maybe a lot of background. So let's start with why I care about this subject. So so if you have a surface, and for me a surface is, in case there's any pedantic people who like to come up with pathological counterexamples, my surfaces are orientable, Hausdorff, second countable. I once attended a talk where the speaker who knew me quite well said, all right, anyone can ask a question at any time except Anschel. So I'm, I understand the kind of questions that come up if you're not careful with these definitions. So given a reasonably tame surface, one thing you can study about the surface is the mapping class group. Which I'll write MCG. There's a number of abbreviations for this. Mapping class group of sigma is the group of homeomorphisms of sigma up to isotopy. Okay, so if you imagine maybe your prototypical surface is this like genus 2 guy, right? The natural, so the homeomorphisms we're not considering, things that we're considering to be basically the identity is if you take like a little disk and, swirl it around in here, do some isotopy of this, you can always spin that back and we'll say that's the same as the identity. The kind of homeomorphism that we are interested in might be one like this. Take a curve, a simple closed curve, and cut around it, and then take those two pieces and twist one of them 360 degrees and glue it back on. So that a path that used to go like that now goes like that. So this gives you a group because you can compose two of these things and undo them. And this group is of interest to people it has applications to 3 manifolds because you can use these to build bigger spaces. It has applications to dynamics, which I guess is straightforward because you're doing a thing and you can repeat the thing. From my perspective, as in much of math, I'm happy to say, okay, this is of interest to someone, and therefore if I study it, someone will be interested in the results. And I stop there. So these are mapping class groups. These have been pretty extensively studied, but they have largely been studied in the case where the surface is one of these guys, your sort of friendly neighborhood surfaces, by which I mean compact or compact except for some punctures. So a surface has, sorry for these ghost lines. I don't know, it's something up with my tablet pen. A surface has finite type. There's a few ways to say this. The neat one that I like is if pi1 is finitely generated. Maybe that's a very geometric group theorist way to think that's simple. Another equivalent thing is if it's compact or compact with punctures, right? And then another way is it's one of these surfaces that fits into the standard classification where you have genus, punctures, and boundary, and each of those is a number, and that tells you everything you need to know about the surface. Okay, these are the finite type surfaces. Infinite type surfaces are everything else. So infinite type surfaces are everything else. Okay, and these also have mapping class groups. And these get called big mapping class groups, which is fun because then you get to call the people who do the other ones small mapping class groups. Right, and just to give you an idea of the kinds of things that can happen here, we have lots of fun surfaces, and they get names. So this guy, which has sort of infinite genus, is called the Loch Ness Monster. Because it has a different homeomorphism type that makes that slightly more obvious. You could do a two-ended one of these. This is sometimes called Jacob's ladder, which I have theological disagreements with because Jacob's ladder starts on earth and goes to heaven, so it should really only have one infinite end. This ladder goes to hell, right? So it's Dante's ladder. But you can also have fun with punctures, right? So you could have, say, a surface with punctures going off to infinity. Again, because I like hyperbolic geometry, my punctures are cusps, but topologically, of course, it doesn't matter. You can also have an infinite type surface with some more interesting structures. So you could, for instance, take an infinite tree and then thicken it and take the boundary of that. So you get a thing like this. That's sort of, there keep being more branches going off forever. And you never get to an isolated puncture, right? The branches keep going forever. This thing is called the Cantor tree because it's boundary, and I'm not going to define the space of ends. There's a reasonable definition of that, which is a Cantor set. Fun fact, if you stop being interested in this and want to think about something slightly related but really different, this is actually homeomorphic to a sphere if you delete a Cantor set. So that's like a cool thing. Okay, so what am I doing with this, and how am I going to justify this as combinatorics? We're going to take these groups and have them act on some object, right? So I should mention that it's not too hard to convince yourself that a big mapping class group is uncountable. which is scary, and topological, which may or may not be scary. So let's have it act on a graph. And then we'll say that we're doing combinatorics. So let's have it act on a graph. And there's some obvious graphs. So you want to pick a graph that has a natural relation to the surface and such that the action of the mapping class group induces an automorphism of the graph. So there's several of these that are well studied. So there's the curve graph. Excuse me. There's the curve graph where we say each vertex of the curve graph is a simple closed curve. Simple meaning doesn't intersect itself. Closed meaning it's the image of a circle. Simple closed curve on the surface, considered up to isotopy. Oh, I should say, please interrupt with questions if and when you have them. I hope that my very informal style makes that obvious, but simple closed curves considered up to isotopy, because again, we don't want isotopies to affect this. And we say that these vertices, what is going on? We say that these vertices are adjacent in the graph, they're connected by an edge if they have disjoint representatives. So these are isotopy classes. You can't, obviously you can always isotope any two curves so that they intersect, but if it's possible to isotope them so that they don't intersect, then they are connected in the curve graph. So I'll draw my finite type surface again, right? So this blue curve and this red curve are connected. And colorblind friendly colors. Oh, that's not an anyone friendly color. This light blue curve is not connected to the red curve, but it is connected to the dark blue curve. Okay, and I've drawn very simple curves, but curves can get very silly. And for finite type surfaces, this curve graph is like an interesting geometric object. It's infinite diameter. It's possible to produce in the language of dynamics. There are mapping classes that have an infinite translation length on this guy, right? So there's a kind of mapping class called a pseudo-Nassov. I'm not going to say what that is right now, but it's not that hard. It turns out, in some sense, most mapping classes have this property that if you apply them to the curve graph over and over, any point moves very far away on the curve graph.
So just to be sure, sorry, these are always infinite graphs, right?
Yes, this is a very infinite graph.
But is it countable still?
Yes, it's countable. There's countably many curves because curve. Okay, if you get rid of simple, each closed curve corresponds to a conjugacy class in the fundamental group.
Okay.
And the fundamental group is countable. So we're taking a subset of the conjugacy classes of the fundamental group.
Thanks.
Right, and that's true even if we pass to even if we move to the infinite type surfaces.
Excuse me, why is it countable if you get rid of simple?
So not every loop in the fundamental group corresponds to a simple curve. So I'm saying if you expand our set, if we take our simple closed curves and we include even the not simple closed curves, just any image
I'm just
of,
saying that if you take the same curve, if you take two curves which are homotopic, but one of them is not simple, then there is no isotopy which maps one to another. So they correspond to different elements in your graph.
Well, so in the graph, I'm only thinking of simple closed curves, and for those, isotopy is equivalent to homotopy. So yes, let's consider that each of these corresponds to a unique homotopy class of closed curve, and there are countably many of those.
Okay.
Yeah, it's a countable graph. It's an infinite valence graph, right? Every curve is has countably many neighbors. So it's not like the best situation that you might want, but it makes things a lot simpler, and there's all kinds of interesting math and geometry around this, right? Unfortunately, in the infinite type case, this fails. Or not fails, but you get much less geometrically interesting, right? And the problem is that I'll go back to the Dante's ladder. If you have you can have two curves that intersect in all kinds of funny ways, right? But since they're both compact things, you can always find a third curve far away from both of them on the surface, which is therefore going to be distance 1 from each of these two. Right. So in the infinite type, this graph, it's still an infinite graph. It's still countable. The same argument applies because the fundamental group is still countable. But this now has this has diameter 2, which means it's not useful for geometric and dynamic kind of purposes. You can still get cool math out of this. This has been used effectively.
So one more question about definitions.
Yeah.
I think I understand that if the curve is null homotopic, then you don't count it as a vertex graph, because otherwise the same argument works in finite surfaces as well.
Yes, indeed, right. Okay. And if your surface has punctures or boundary, you need to also specify that it's not peripheral. Yeah. That is exactly the kind of question that I would ask. Take that as you will. So, all right. So for infinite type surfaces, this guy maybe has some faults. Another option, which you can do, is an arc graph or a loop graph. So suppose we insist that our surface has exactly one puncture. So let's look at has a unique puncture. And by puncture, I mean a point that you could add, a place where you could glue in a single point, and then that area would be compact. So like these guys, excuse me, like these guys, that's a puncture, right? But not one of these infinite ends. Right? Then we can talk about embedded arcs instead of curves that have their endpoints at that puncture. So the loop graph of sigma is the graph whose vertices are isotopy classes of loops terminating at the puncture. And the same edge condition, right? Adjacent if they have disjoint representative. Okay, and now we can ask again about this graph, again, by the same argument. This time, we're not even conjugacy classes, right? This time, each one of these corresponds to an element of the fundamental group. If you replace that puncture with a base point, there's countably many of them. But this time, this does have infinite diameter, right? So this still has infinite diameter in the infinite type case, right? And it has a nice action of the mapping class group in the sense that not only does the graph have infinite diameter, but you can find elements of the mapping class group that have, legitimately infinite dynamics, that if you pick a point and apply the mapping class over and over again, it gets farther and farther away, which again is of interest. And at some point, the existence of such a graph for any mapping class group was an open question. I should say this definition is due originally to Juliette Bavard, and then it was expanded to more surfaces by am I going to remember the people? Ramayana. Do not quote me on these citations. Okay, so okay, it's been less than half an hour and we're approaching the end of the background. That's actually fine. So right, if we have an action of the mapping class group, that means we have an isomorphism from the mapping class group of sigma to, I'll put an L for loop graph. Sorry, we have an action on the loop graph, so we have homomorphism from the mapping class group to the automorphism group. And the natural question to ask is this an isomorphism, right? Another way of saying that is, does the loop graph contain all of the topological information about the surface, right? If this is an isomorphism, that means any question you wanted to ask about the mapping class group, you can actually ask about automorphisms of this guy. And since the mapping class group somehow captures the topology of the surface, if you don't care about isotopy, which in many cases you don't, that means that the loop graph also captures the topology of the surface. So I have to do one technical thing, which is normally when we say mapping class group, we're only counting the orientation preserving homeomorphisms. Not for any good reason. It's just an index 2 subgroup of the one that contains all of the homeomorphisms. which when we're being careful, we put a little star here to say that this is the extended mapping class group, the one that obviously an orientation preserving homeomorphism will also give you an automorphism of the loop graph. Okay, so the really interesting question is, does this give you an isomorphism? And one direction is pretty easy. So injectivity turns out to be basically free, because so if some mapping class group acts on the, if some mapping class, excuse me, acts on the loop graph as the identity, in other words, it preserves every loop. Well, then by just pulling those loops off of the puncture, then it has to also preserve every curve. Right? If you preserve every loop, then well, let me be careful. You preserve every curve on the slightly different surface you get from filling in the one puncture. Right? If you move every loop to a loop that's isotopic to that same loop, then you've also moved every curve to a curve that's isotopic to that same curve. Right? So if it preserves every loop, then it preserves every curve, right? Up to isotopy, right? So we're not done, because you could worry that moving all of the curves by an isotopy somehow messes up the whole surface, but someone else has solved this problem. Israel Morales. Oh, I'm not going to get these in the right order. Oh, well. Pretend I wrote these in alphabetical order. This was shown that in that case, phi must be the identity. Okay, so if you fix every loop up to isotopy, in fact, you're isotopic to a homeomorphism that just fixes everything point-wise spot on. Okay, and this involves a somewhat careful argument that I cannot take credit for. What I can take credit for is the other side, surjectivity. Surjectivity. So suppose F is an automorphism of the loop graph, right? We want a homeomorphism phi such that when phi acts on the loop graph, we get F. In other words, phi of lambda is isotopic to F of lambda for every loop. Okay, our goal, if we can build such a homeomorphism, that shows surjectivity. So that's going to be our goal for the remainder of this talk. We have an advantage here, which is that this question has been answered positively for finite type surfaces. Okay, so I I always think this is right. Ermac and McCarthy in like 10 years ago. I guess it's more than 10 years now. Time is imaginary. Ermac and McCarthy did this for finite type. And here is an outline of their proof. They say, okay, first, pick a triangulation which is just a maximal set of loops. Okay, and the reason it's called a triangulation is that if you make a maximal set of loops, what's left, if you make a maximum set of loops and cut along them, everything you're left with is a triangle. Right? Because if you're left with anything more complicated than a triangle, you could draw an extra loop in it to cut it into smaller pieces. Keeping in mind, right, these are triangles with all their vertices at the same point, which makes them a little hard to picture. But if you have a more complicated surface, you can always draw if you have a more complicated surface with a puncture in it, you can always draw a loop, a non-null homotopic loop from the puncture to itself that cuts the surface into smaller pieces until you get down to triangles. Right. So, and then we pick a triangulation, show that after we apply our automorphism to this triangulation, it's still it still gives us triangles. Right? In other words, if you take 3 loops that form a triangle and you do an automorphism of the loop graph, you get 3 new loops. A priori, these are just 3 disjoint loops, right? They might not form a triangle, but they show that in fact they do form a triangle. In other words, that the information of the loop graph, right, of what other loops intersect those 3 is enough to convince you that they form a triangle. Okay, and now we have a map from triangles to triangles, and we glue the triangles together. Okay. Now, we can sort of copy this, and we can reuse their thing. So, for instance, the fact that the fact of being a triangle is preserved by the loop graph, that proof doesn't depend in any way on the surface being finite type. It's an entirely local thing to do with constructing other arcs. Right? Basically, what does it mean for 3 arcs to join a triangle to form a triangle? This is going to be very hand wavy, right? If these 3 guys form a triangle, what that means is that any arc that passes through this guy has to also pass through either this guy oh dear. Hold on a second while I deal with technical issues. Okay. Has to also pass through either this guy or that guy. There's no other way out of the triangle. Right? So that sort of convinces you that you can get convinces. Obviously, the argument of the paper is longer, right? But arguments like that and some other ones for some edge cases are used to show that the property of being a triangle is preserved under automorphisms of this graph. So then you map each triangle in the original surface to a triangle in the new surface, and you glue them together, and that gives you a homeomorphism. Okay. So we can use all of this. The big problem is that triangulation is no longer nearly so nice a creature as it was before, right? So a triangulation, right, by which I mean a maximal, oh, I should say maximal set of disjoint loops here. Set of disjoint loops can be really, really weird in an infinite type surface. What I mean by this is it's no longer at all clear that the complementary regions of such a thing are triangles. Okay, the triangulations exist if I define them as a maximal set of disjoint loops, because I can just apply Zorn's lemma. And maybe since it's countable, I don't even need Zorn's lemma, but I don't want to try and think about those things. But these things exist, right? But because there's room for topology on this surface, you're going to have some complementary regions that aren't triangles. Like if you take, so we had the Cantor tree before, we have a similar thing, which is more useful for us, the punctured Cantor tree, where we put a puncture at the bottom. Right, so consider a triangulation that includes loops that go up here. What is going on? Excuse me. That include loops that go up here and like loop around one of these guys, right? And then we can go up inside of this loop and loop around a higher one. And we can have these nested loops, okay? And we keep doing that forever. There's a sort of an arc starting at the puncture and going off towards an end that lives inside of those loops. It's never included in any loop. Therefore, it's a complementary region. But it's also very much not a triangle. It's a line. It's an infinite line. So if we're not careful, something will go wrong. At the very least, we certainly can't just say, oh, it's all triangles, stitch them together. Something more important has to happen. Something more interesting has to happen. But we have an advantage, which is that Ermack and McCarthy have left us with a sort of embarrassment of riches, because their argument says, pick any triangulation, right? But it doesn't have to. We can pick our triangulation. We can choose a good triangulation that has exactly the property that we want. Okay, and so that's going to be the plan. We're going to pick a good triangulation. And I'm not defining good. By good, I just mean a triangulation that will make our proof easier. Okay, and the goal will be that our triangulation breaks down the infinite type surface in such a way that all of the that we can break it into finite type pieces and apply the result of Ermack and McCarthy one at a time. So the first step is to make what we call a pants decomposition. Which, if you're not familiar with surfaces, the surface with 3 boundary components is called a pair of pants because you can draw it like this. And if you're American, this is a reasonable name for this thing. If you're British, I apologize. This is a pair of pants, and any surface you like, as long as it's not one of the really simple ones, can be cut up by simple closed curves into a countable collection of pairs of pants. And here's where, if you're following along with the pedantry, here's where we're using the fact that our infinite type surface is second countable. Otherwise, that would not work, but it is. We're fine. We can cut everything up into pairs of pants. And we're just going to insist. Okay, and for our purposes, we're going to treat the puncture as just a kind of marked point when we make the pairs of pants. So one of our pairs of pants just has like a little rip in it. And that's our puncture. And because our surface is made by putting these pants together, and it's a countable collection of pants, we can insist that we put our pants together in such a way, so we'll call them pi 1, pi 2, etc. And we'll make sure that the union of these guys is always connected. And the puncture is in pi 1. Okay, and let's give this a name. Let's call this sigma k. Okay, so now we have a sequence of finite type surfaces called sigma k that exhaust sigma, right? So sigma k exhaust sigma. Okay, so now our good triangulation is going to have the property that if we cut it off at regular intervals, it restricts to a triangulation of sigma k. Okay, and the way we're going to do this is we're going to build our triangulation inside of the pair of pants. When should I be planning to stop this talk?
So the next talk starts at 1:15. We might want to have a small bathroom break before, but I mean, you still can go on for like 5 or 10 minutes if you want.
Okay, got it. So I'm trying to decide. Yeah, okay. So I'm gonna spend the remaining time talking about how I construct this good triangulation and not say the final bits of how having that lets it work. But right, the idea is if you can construct this good triangulation, then you can map each sigma k to a subsurface that is homeomorphic to sigma k, and then build up in this way and get your whole homeomorphism. So let me talk about how I build this thing. So in terms of these pants, there's kind of 3 kinds of pairs of pants, right? Notice that by the ordering, we're always attaching pairs of pants to the surface that already exists. So we can specify that that we can measure a pair of pants by how many of its boundary components are connected to the pre-existing thing. So we kind of have 4 options, right? We have when we start out, what am I doing? Okay, when we start out, right, our first pair of pants has the puncture in it here. And 3 boundary components not connected to anything. Later on, we might sometimes attach one. I'm imagining we're sort of building this thing up like this in a kind of way that it hints at Morse theory, although there isn't actually any Morse theory here. But we might have one leg already connected, right? We might glue on a pair of pants that's the opposite of that, where we have 2 legs already connected. And we might have 3 legs already connected, right? We might just be capping something off. Okay, these are our 3 kinds of pairs of pants, and we're going to build a tree, which we're going to embed in our surface, and which will make it easier to draw these loops, right? So you can't draw a loop just in one of these pairs of pants. Every loop has to go down to the base point, but we're going to specialize how we get down to the base point. So this thing I call the skeleton, and I'm just going to draw it on each pair of pants. So on the first one, it goes up out of all 3 of these guys. If we get to this situation, it goes like that. If we get to this situation, we want this to be a tree, so that one will just stop there. And likewise, if we get to this situation, we'll just stop there. Okay, so this gives us in red the skeleton, which is the which is this tree embedded in the surface. Okay, and now we can draw arcs. Sort of, we can
just a very
loops.
small question, if I may. You don't care which one of the 2 you stop at. That's arbitrary, or
it's completely arbitrary.
Okay, thanks.
The goal is completely arbitrary. The goal is to decide once, so that everything we do afterwards is compatible.
Okay.
Yeah, it's completely arbitrary, right? And this pants decomposition. There's infinitely many ways to do the pants decomposition that will give you a different skeleton. Right. So we're even here. I guess we're not actually picking just one triangulation, but we're insisting their triangulation has a nice property. One of which is that it's based on the skeleton. So we when we're actually in the middle of this thing, right? Say we're in this situation. We're somewhere deep in our surface. We have our skeleton. Okay. If I say this loop, okay, instead of drawing the loop down to the base point, down to the puncture, I'll just draw a loop as an arc connecting 2 points on the skeleton. And then I'll say, well, what I actually mean is follow the skeleton all the way up, right? Then follow this blue curve, then follow the skeleton all the way down, right? And now 2 disjoint arcs on this that connect points on the skeleton to each other will always correspond to disjoint loops. So now we can draw loops on the whole thing by just thinking of loops on the skeleton. Obviously, not all loops have this form, right? But because the skeleton is a tree, we've uniquely determined them. Okay, and now I just need to say, how are my loops going to be drawn on these 4 types of surfaces, of pants? And in fact, from the point of view of the skeleton, the first 2 types of pants are the same. So I only have 3 places where I have to figure out how to draw them. And So I am not going to try and reproduce these in real time. I will show you these pictures. So in the simplest case, right? So I've drawn this 3 times, right? Once in the way I was showing you the pair of pants. Once in this other sort of flattening of the pair of pants. The middle picture is homeomorphic to the picture on the left, and then the picture on the right, I've sort of shown what happens if you shrink down the skeleton to a point to convince you that this is really a triangulation. And then the pictures get more complicated for the other surfaces, but not like there's no magic here. I'm making sure that there exists one arc which is parallel to each of the boundary components, and then I'm filling in the rest. And it gets even more complicated, but not in an interesting way. And the end result of this, and then I will stop, is that if you take the loops built up out of the first k pairs of pants, then those loops fill the surface sigma k. So loops built from k pairs of pants fill the surface sigma k. And in particular, that means that we can choose as our image of sigma k the surface filled by the images of the loops in those first k pairs of pants, and that gives us nice finite type things to work with, and we can apply the Ermac and McCarthy result. And that is slightly more than the time I was given, so I will stop. Thank you very much.
All right, thank you very much. Are there any questions? That doesn't seem to be the case, so I'll stop the recording.